Hey guys, welcome back to another video of electrochemistry. This is going to be the last video of this series, and in this video we're going to learn about change in Gibbs free energy, that is how to calculate the change in Gibbs free energy in electrochemistry, that is in case of electrochemical cell or an electrolytic cell, the half cell equation, that is the half cell reaction. In those cases, oxidation or reduction, how to calculate the change in Gibbs free energy, right? So for that, we're going to use a specific formula for either of the half cell reaction. That is, del G, change in Gibbs free energy, is going to be calculated using this formula, minus N. N is the number of electrons transferred, times your cell potential, that is your reading on the voltmeter, your resultant potential difference between two electrode potentials, E cell. So cell potential times Faraday's constant. Okay, so this is going to give you the change in Gibbs free energy. You don't need to understand where this formula is coming from for this syllabus, but you need to be able to calculate the change in Gibbs free energy, right? So you'll find out, let's look at an example to understand how to use this formula, right? So the question is calculate the del G for the following cell reaction. And this is what's happening, right? So over here, notice this is the entire ionic equation between two electrode reaction. That is, if I draw it, I'll shortly draw it. So you have one made up of Mg electrode solution. What should be in the solution? In 2 plus. What should be the concentration? 1 mole per dm cube. Use a voltmeter. Connect it to what? Calcium electrode. Okay. So connect it. Oh no, not calcium. This is copper. Sorry. So this is going to be a copper electrode. And this is going to be your copper solution, Cu 2 plus 1 mole per dm cube. Don't forget to add a salt bridge, right? Fair enough. So from these few information, I generally know it from the top of my head that magnesium is more reactive, so it's supposed to have a more negative electrode potential, I believe. Yeah. So minus 2.38. Correct. So more negative. What does that mean? More negative means, comparison to copper, by the way. Copper is more positive than hydrogen as well. So positive 0.34 electrode potential. So in case of the magnesium, notice more negative, therefore it wants to release its energy. Therefore, in this case, oxidation is going to take place. So you're going to see a backward arrow. That means in this case, oxidation take place, right? It's going to release the electrons since high negative electrode potential. In case of, notice the copper, it has a more positive electrode potential, so it wants to gain electrons. Therefore, forward reaction. Again, remember, all your electrode potential equations should be written in the form of reduction. Okay. So for copper, forward reaction. For magnesium, backward reaction. What is, by the way, so for this, oxidation is taking place, ox, and for copper, reduction is taking place, red. Fair enough. So we know the oxidation and reduction. So now, if we calculate the cell potential, what is the cell potential going to be? So take a wild guess. It's going to be electrode potential of the reduction minus electrode potential of the oxidation. So that's going to, which one is getting reduced? Copper, yeah. So positive 0.34 minus 2.38, right? So this is going to be a cell potential. So 0.34 plus 2.38, whatever it is, that is going to be a cell potential, overall cell potential, right? So what is the change in electrons, by the way? If you don't know, if let's say it was like potassium plus 1 electron turning into potassium solid. In this case, so if instead of magnesium it was copper, why do I say copper? Calcium, potassium. So in case it was potassium, right? Notice this is not balanced. Copper and potassium is not balanced in terms of the transfer of electrons. So in this case, you need to balance it, right? So anyways, in this case, we have a balanced reaction, that is the transfer of electrons are balanced, right? So what do we do in this case? We know the transfer of electrons to be two electrons. Next, find a change in, that is your your cell potential. So find your cell potential, that is going to be, as mentioned, 0.34 plus 2.38, right? And that is going to give you whatever that is going to give you. So 0.34 plus 2.38, 2.38. What is it? 2.72, I believe. 2.72. So this is going to give you 2.72. Okay. So change of electron, cell potential, and Faraday's constant, F from the equation, F over here, right? So times F, and the product of all this is going to be your change in Gibbs free energy. Now, another thing, using this, you will also check the feasibility of the reaction, right? So your change in Gibbs free energy in this case is going to be negative. Why? Because this reaction doesn't indeed take place. Meaning, notice the magnesium is indeed getting oxidized as per our electrode potential arrows. So as per our electrode potential arrows, magnesium is supposed to be oxidized, and magnesium is indeed oxidized, and copper ion is getting reduced. So both of those are happening correctly, which is why your reaction is feasible. So your del G is negative. Negative means feasible. You should know that from entropy, right? Now, what if the equation was Mg2 plus Cu not ferment, okay, Mg plus Cu2 plus. Okay, now in this case, notice it's getting reduced and this is getting oxidized. However, our arrows don't match, right? So how, if you remember from the video where I talk about how to check feasibility of a reaction, you would find the E cell of this and you would notice. So E cell of this reaction is going to be, which one is arguably getting, according to this equation, which one is getting oxidized? Sorry, which one is getting reduced? Mg2 plus is getting reduced, right? So you're going to write minus 2.38 minus, and copper is getting oxidized, so 0.34. Notice how in this case your cell potential is going to be negative, right? So since your E cell is negative, this reaction is not feasible. Why is it not feasible? Now see, because if you input this into the del G formula, your del G formula is minus n E cell times Faraday's constant. So minus times 2 electrons times your negative value times Faraday's constant. Now notice this this negative and negative will cancel out, and your final del G value will actually be positive. This is why if your what do you call it? Cell potential is, what do you call it? Wow, negative, right? So if your cell potential is negative, this is why your reaction is not feasible, because your change in Gibbs free energy is going to be positive, right? So since your change in Gibbs free energy is positive, the reaction won't be feasible, right? So using this formula, you can also check the feasibility of a reaction. Okay, so yeah, this is how you use the formula del G. Remember this formula and the one we discussed in the previous video. Wrote this, sorry. Yeah, this. So remember these two formulas. These are going to be very important for, I don't see these coming very often, but usually they ask you to calculate the cell potential more often than not. But yeah, do remember these two formulas. And that is going to be it for electrochemistry. So I'll try to solve a few other questions and see you in a new series.